Hello friends, in the last video we have seen how to analyze motion in 1D, that is motion along a straight line, and this straight line can be x-axis, that is a horizontal axis, or it can be vertical axis, that is the y-axis. So in that video we have learned how to analyze, how to determine its position at given point of time t1 and how to determine its velocity at any point time t1. For example, let's say if I have an object and this object is moving along this axis. So this is my x-axis. So this object is moving along the x-axis. So when I am analyzing this object, so this is a straight line motion. So object is going in this straight line. So this is a straight line motion. So this is an example of one-dimensional motion. So what is my objective? My objective is to find at any point of time, let's say t is equals to t1, what is its position? That is what is its x coordinate. So I am interested in x coordinate of this object. That is what is the position of this object. And I am also interested what is the velocity. That with what velocity this object is moving at any point of time. So these two are point of interest. First is position and the second is velocity of this object, and that was the one-dimensional motion. Now extension of 1D motion is 2D motion, that is two-dimensional motion, and two-dimensional motion happens in plane. So if you see in one-dimensional motion happens on a straight line. In two-dimensional motion, basically motion takes place in a plane. So what do you mean when I say plane? Basically when we say plane, it consists of two axes. Here in this case I have a x-axis and in this case I have a y-axis. So now using these two axes, now we have a plane. So this is my plane. So now motion will happen in this plane. Then we will call this is a two-dimensional motion. Now in 2D, motion can have a different type of path. It can either go in a straight line, something like this. So this is a straight line motion in 2 dimensions. It can go something like this, parabola. We will call this as a projectile motion. It can also move in a circular path, or it can go in a zigzag fashion, something like this. So all this is an example of two-dimensional motion. So you see, only important point when we are saying two-dimensional motion, this motion is happening in a plane. They will have different kind of path. So it is not either along the x-axis nor along the y-axis. It has a path that moves along the plane, that moves in the plane. So let us discuss some example of two-dimensional motion. The first example of two-dimensional motion is a projectile motion. You might have seen these games called cricket. In these games what we have a batsman and we have a bowler. So this bowler, what he does, he throws a ball and this batsman hits this ball. Now the path of this ball is basically example of projectile motion. So this bowler throws this ball and this goes in a plane. So this is not moving in a straight line. It's moving in a plane. So you see, this is a vertical plane. So this ball is moving in a vertical plane. Similarly, when this batsman hits this ball, this goes something like this, then this is again a plane. So this is a two-dimensional motion. So in such kind of motion, we are interested in at what velocity bowler should throw the ball so that it reaches very close to the batsman. And other word, he is also interested with what angle he should throw, with what velocity he should throw, where should the batsman at what velocity he should basically hit the ball, and in what direction he should hit the ball. So we are interested in magnitude as well as direction, and this all happening in a two-dimensional motion. So projectile motion is an example of two-dimensional motion. Similarly, when you play the football game, this is also an example of two-dimensional motion. So at t equals to 0, this ball is here and you hit this ball in this direction and this goes something like this. So in this case you are interested in at any point of time what is the x coordinate of ball. So this is the x coordinate of ball. So this is where your ball is from the origin, from the point where hit the ball. So this is your origin, that is 0 0 coordinate, x coordinate is 0 and y coordinate is 0. So in such kind of problem we are interested in where the ball is exactly at given point of time. This means what is its x coordinate and what is its y coordinate, what is the height from the ground and what is the distance from the origin. So this is the coordinate, in this case x coordinate and y coordinate. And we will also be interested what angle he should basically hit the ball, with what velocity he should hit the ball, and if he has a something in mind, some target is in the mind, goal post is in the mind, then he should know. From experience all this comes. Basically he doesn't have to do all this calculation, this comes from the experience. He has the experience, he knows with what velocity he should hit the ball and with what angle he should hit the ball, and so all this comes with the experience. And this is an example of projectile motion. Another example of projectile motion, another example of 2D motion is circular motion. So this is circular motion. So you might have some time on the roller coaster. So this is in this kind of game, or you can say entertainment. What you do is you have some buggies and you basically go onto that buggy, and that buggy goes from crest and bottom, and then it all moves along a circle. So you see what happens, this object is moving along this circle and then finally it goes to the next track. Same thing, it comes and moves. So this object is moving in a circle. So this is an example of circular motion. So what is happening in this case? This case, you see all this is moving in a two-dimensional vertical plane. So this motion basically contained in a plane, and the path or trajectory is a circular motion. So this is an example of 2D motion, because you have a plane in which this is moving. This is not moving in a straight line. It's not like this, or it's not like this, or it's not like this. So it is not moving in a straight line. It's basically moving in a plane, and in this case trajectory is a circular motion in this case. You can have a three-dimensional motion also, just to illustrate not only 1D, 2D, it is also possible to have a motion in 3 dimensions. For example, if you have something a spiral, later we will learn in magnetic field, the particle moves something like this. So they are something, this is kind of motion is called a spiral motion, something like this. So this is moving and going. So if you consider, this is a superposition of circular motion, but only thing is in this case, every time circle is not in the same plane, it's moving. So in this case the motion has 3 components. It has x component of velocity, it has y component of velocity, and it also has a z component of velocity. So when I say motion in 1 dimension, it has only 1 component of velocity, either vx, vy or vz. When I say motion in 2 dimension, it basically has 2 component of velocity, vx or vy, vx and vy, or vy and vz, or you can have vx and vz. So 3 possibility. You can have vx, vy, you can have vy, vz, you can have vx and vz. So these are the 3 possibility when you have a motion in 2 dimension. Now when you have a motion in 3 dimension, you will have x component of velocity, you will have y component of velocity, and you will also have a z component of velocity. One example is a spiral motion. You might have seen this mouth ka kuwa, or the dip, this is a death well sometimes called. So people basically try to drive a car on a spiral motion. This is example of 3D plane. So 3D motion. So you see this is going in a circle, and then it comes, next time it goes up, next time goes up. So this is the motion that takes place. So you see in this case these cars basically moves in a spiral motion, and that is the example of 3D motion, because it is going in the vertical direction, in this direction as well as in this direction also. So such are examples of 3D motion. In the 3D motion you have to find position of object in terms of x coordinate, in terms of y coordinate, and in terms of z coordinate. So when you have this, you have to give x by z coordinate, you have to give vx, vy, vz. So now you understand, when I have one dimension motion, this is easy. So you have to give only one Cartesian coordinate position, either x, y, or z, and then you have to give only one velocity. It can be vx, vy, or vz. Now in this chapter we will also learn about the relative velocity. So in the next few videos we will see what all this means, what is circular motion, what is projectile motion, what is relative velocity. So just to illustrate relative velocity, when you sometime might be having in a train and some other train is moving just side by yourself. So you find that train is either moving fast or it can be moving slow. So basically what you are doing in that case, you are observing another train with respect to your velocity, with respect to your position. So you are not standing. Your train is also moving and the next train is also moving. So both train is moving, both positions are changing. So now in those cases, we cannot talk simply about in terms of absolute position, absolute velocity, because your velocity is not constant and you are measuring the velocity of other train. So you can max say something about relative. What is the relative position of that train or that guy that is sitting in the train with respect to your velocity or your position? Because you are not constant, you are moving, then this is an example of relative velocity or relative position. So when we say relative position, that means what is the position of other guy with respect to your position. So in the next few videos, we will also see how to calculate relative velocity, what is the use of relative velocity, and how we do problems related to relative velocity. So in the previous chapter, we have learnt about different terminologies. That is, first is displacement, velocity, and acceleration. So if you remember previous videos, we have said if you have a motion in one dimension, you have to know what is the displacement, what is the position vector. Displacement means position vector, where it is from the origin. So displacement, velocity, and acceleration. So now in this video or in the next few videos, motion related to two dimensions, we are going to illustrate those terminologies again. Only thing is, this time we will have position vector in two dimensions. Position vector, if I have a two dimension, then velocity will be having two components. Similarly, acceleration will have two components. So we can say now these quantities, that is displacement, velocity, and acceleration, will not lie in a single line. They will be in a plane. They will have two components. They will be having two components. So we summarize, if you have a motion that is in a plane, we call this a two-dimensional motion. And there are different kinds of motion that is possible in two dimensions. You can have a projectile motion, you can have a circular motion, you can have a three-dimensional motion. An example is a spiral motion. Now we will study some terminology. First is position vector. Now what is position vector? One thing is, it is a vector. That's why this is called position vector. And position, the term position means where the object is located. What is the position of that object? So when I say position vector, this means I want to know where the object is located, what vector I can describe the object. So to describe the motion of a particle in a space or in a straight line or in a plane, that is two dimension, we must first be able to describe the particle's position. So we should know where the position of the object is, and that is called position vector. For example, if I have an object that is moving in one dimension, so this is my x-axis. So object is moving in the x direction. So this is my object and this is moving at some point of time this object is here. So this is t is equals to 0 and this is t is equals to t1, and this is x equals to 0 and this is equals to x1. So this is position vector. So I can say position of this object at t equals to t1 is equals to x is equals to x1. So in this case this is the vector. So this is a one-dimensional vector. So position is here and this is origin from where it started. So if I connect the final position, that is t equals to t1, with the origin where it started, that is t equals to 0, we get a vector. So this is my position vector, and in this case this is simply x vector. So generally we denote position vector with symbol r, and arrow sign onto the top of the letter denotes this is a vector. So position vector in this case has only one component, x component. You can also have a motion that takes place in two directions. For example, let's say this object started at t is equals to 0 and t is equals to t1. This is the position of this object. Now it has two components. So this object, I can say this has some x component and this has some y component. So this is the y component of position and this is the x component of position. So this is the x-axis and this is the y-axis. So what is the position vector? As I said earlier, once again, you have to connect the origin with the final position of the object. So this is the position vector. So this is my position vector. So I can say this point is A and this point is B. So vector AV in this case is my position vector. In fact, I can write this position vector in terms of Cartesian coordinates and using the unit vector. You may remember when we discuss vector chapter, in the x direction we generally use unit vector I cap and in the y direction we use unit vector j cap. So this distance or this vector r is nothing but sum of x vector, that is xi, and y vector. So this is my x vector and this y is nothing but yj. So this is my bi-component vector. So if I want to calculate this vector, so this vector is nothing but sum of this vector plus this vector. So I can say vector r is nothing but sum of xi plus yj. So if I have a motion in two dimensions, I can denote position vector simply xi plus yj. Now what about if I have a motion in three dimensions? This is the extension of the previous case. Now you understand, if you have a motion in the three dimensions, you will have x component, y component and z component. And then how will you denote the position vector? You will basically denote the position vector as xi plus yj plus zk. So only one thing we are changing, that we are adding third component. To illustrate this, let us say I have an object and this is here at t is equals to 0 origin, and this is my x-axis, this is my y-axis and this is my z-axis. So these are the three axes. Unit vector along x-axis I, along y is j cap, and along z this is k cap. Now at certain point of time this object has reached to this position, that is position P. So it has started from O origin and it reached to position P. So what is its position vector? As I said earlier, you have to connect the origin with the final position. So in this case, this is my position vector. Now I can write this position vector as sum of three vectors. First, if I take xi and yj, if I sum these two vectors, I will get a vector that basically passes through this plane. So this plane, you see, in this case we have a plane. So on this plane I have a vector that is this vector. This vector is nothing but xi plus yj. So xi plus yj will give this vector. Now if I sum further, so I basically sum this vector and this vector, I got a vector something like this, that is on plane xy. Now if I add z vector, that is zk, so this is my x I cap, this is by j cap, and this is z k cap. So if I add z j cap, I will basically have this vector, and that is nothing but xi by j plus z k cap. So I can say if I want to write position vector in 3 dimensions, I have to basically sum all the components with corresponding unit vectors. So now you understand, finding position vector is not a difficult task. What you have to do is, you have to simply first find the coordinates. What is the coordinates of that vector? That is x component, y component, and z component. This component, this component, and this component. Once you know these 3 components, you can write position vector. That is r vector. Now let us discuss about average velocity, and this will discuss in 2 dimensions. If you remember, in 1-dimensional video we discussed displacement, or the average velocity is nothing but displacement divided by time interval. That is, average velocity V average is equals to displacement, that is delta x, divided by time interval dt. That we learned in the previous chapter, that is in 1-dimensional motion. I can further basically generalize, since the motion is happening in 2 dimensions, it can also happen in 3 dimensions. We can replace this x with the position vector. That was basically position, x was position. So now what I can do is, I can replace this position vector. So now I can say change in position vector divided by time will give you the average vector. So this can be written here. Let's say I have an object. This object at t equals to 0 is here, and sometime t1, this is at position p1, so this is position at time t1, and this is position at time t2. So this is the position of object. Object is at position p1 at time t1 and at p2 at time t2, and I am interested to find what is the average velocity in this case. So what I will do is, first we will find position vector of p1. So what is that? Simply I have to connect the origin with the final position. So this is my position vector. That is r1 vector. That is position when the object is p1. Similarly, what is the position vector when the object is at point p2? So this is the position vector. When the object is point number 2, that is p2, that is vector is r2. So position vector is r2, and we put a arrow sign on the top to show that this is a vector. Now what we said average velocity is defined as change in displacement or change in position vector divided by time interval. So in this case, what is the change in position vector? So initial is r2, that is final is r2, and initial is r1. So we have to basically find change, that is r2 minus r1, and then we have to divide by the time interval. In this case, time interval is t2 minus t1. Now this term that is on the top, r2 minus r1, is nothing but change in position vector. So let us try to see this once again. Now this is r1 and this is delta r. So this is change in position. So if I use this triangle O, P1 and P2, I can write r1 plus delta r, and this is equals to r2 vector. So what I am using here? I am using sum of 2 vectors is equals to third vector, that is vector r1 and vector delta r, and if you sum these two, you will get the third vector, that is vector r2. So from here I can write delta r is nothing but r2 minus r1. So now I can plug this vector, that is r2 minus r1 is nothing but delta r. So r2 minus r1 is nothing but delta r, that is delta r vector. So, and this divided by delta t. So now I can write velocity, that is average velocity, is nothing but simply change in position vector, that is delta r divided by delta t. So in this case, this is the change in position vector, and then I have to basically subtract this. If I want to calculate delta r, I have to subtract r2 minus r1, that is subtract r2 and r1, and then divide by delta t, and then you will get the average velocity vector. So what about average velocity vector? Whether it's a scalar or it's a vector. You see, this is a vector quantity. Why this is so? Why this is so? Because we are calculating velocity average is nothing but change in velocity, change in position vector divided by time. So velocity average is a vector quantity. You see, what we are doing is we are simply multiplying delta r vector with 1 by delta t. So this is your average velocity. So what we are doing is we are multiplying delta r with a term 1 by delta t. So this is a vector quantity and this is a scalar quantity. So this is nothing but you are simply multiplying the change in position vector with a scalar quantity, and that's why the average velocity will be a vector quantity. So calculating the average velocity is simply change in position vector multiplied by a scalar coefficient. Now if you have a one dimension, things becomes easy. You simply write average velocity is equals to position x2 minus position x1, and is divided by t2 minus t1. Once again, this average velocity is in the x direction. Since I know the direction, that is in the x direction, we know this is a vector quantity. Now next we will discuss a term called instantaneous velocity, and this is related to average velocity. When you calculate the average velocity, you require two times, time t1 and time t2, and then you calculate the difference in time, that is change in time, delta t, time interval. Now this time interval can be very large, or it can be very small. So instantaneous velocity is basically limit of average velocity, limiting case of average velocity when delta t tends to 0. When delta t becomes 0, we define average velocity as instantaneous velocity. So it is the limit of average velocity as time interval approaches 0, it is equals to instantaneous rate of change of position with time. So instantaneous velocity is nothing but instantaneous rate of change of position with time. So when your time is very small, that is 0.0001 second or even less than that, in that case your average velocity becomes or tends to instantaneous velocity. So let us try to see using this figure. So this is position of object at time t equals to t1, that is p1, and corresponding vector is r1, and this is position at time t2, corresponding vector is r2, and in this case r1. So delta r, that is change in position vector, is nothing but r2 minus r1. So this point is here and this point is here. Now if I decrease delta t, what will happen? Sometime this point will be here, so p2 will be here. Depending upon time, if I take even a smaller, P2 will be here, P2 will be here. In that case, your delta R is becoming a smaller and a smaller. And a limiting case will come when this is very close to here, somewhere here. So this, in that case, delta R is only this much. So this is your R2 and this is your delta R. So your triangle is becoming a smaller and a smaller. So this is R1 vector, this is R2 vector, and this is delta R vector. So as time basically tends to 0, or you take a smaller and a smaller time, the change in position vector becomes smaller and smaller, and point P1 and point P2 are coming close to each other, and in those cases we define instantaneous vector, that is instantaneous velocity. So this is your average velocity. So this is the expression for average velocity. change in position vector divided by time, that is time interval. And then this term, that is limiting delta t tends to 0. So limit delta t tends to 0. It's saying that now delta t is becoming a smaller and a smaller, then delta r is also becoming a smaller and a smaller. In that case, I can write very small change interval of time is dt. So dt is very fraction or a small fraction of change in time. And similarly, delta r or dr is basically very small change in position vector. So if I object here, so this is my position vector, and if this changes with very small amount of time, in dt time, if this changes by dr, then we define instantaneous velocity is equals to dr divided by dt. So you see, dr vector is becoming a smaller and a smaller. A time will come when point P2 and point P1 will basically coincide very close to each other. That point of time is basically your instantaneous velocity. So you can see, you can measure instantaneous velocity by taking delta t as small or even larger. So your accuracy will depend upon what is the value of delta t. If this is very small, in that case you will get exact instantaneous velocity. If the delta t value is large, in that case you will get relatively inaccurate, or result will not be that accurate in that case. So you have, if you want to calculate instantaneous velocity, your delta t or dt time should be a small. So as I said, instantaneous velocity is a vector quantity. So the magnitude of vector at any instant is the speed of particle at that instant. So what is the magnitude of instantaneous velocity? That is, you have to simply take magnitude of instantaneous velocity. That is nothing but what is the speed at which speed the object is moving. So instantaneous velocity is a vector quantity. It has two things. One is the speed, another is direction. That is magnitude and direction. So how do you calculate magnitude? So magnitude is simply a speed of the object. At what speed the object is moving at that point of time is called basically magnitude of instantaneous velocity. Similarly, the direction at any instant is same as the direction in which the particle is moving at that instant. So when we want to find what is the direction, then this is simply the direction of motion of particle, that is the instantaneous velocity direction. So if you want to find the direction of particle, so you have to see simply in which direction the object is moving, in which direction the particle is moving. That will give you the direction of instantaneous velocity. So to conclude, at every point along the path, the instantaneous velocity vector is a tangent to the path at that point. So this is important. As I said, if you basically choose point P2 very close to point P1, then you define instantaneous velocity. So if your point P2 is coming very close, because delta t or dt becoming a smaller and a smaller, what will the position? At this point, the object is moving in this direction, and this point is coming close and close. So this means in this direction, this is the motion of the object. So if you want to find the direction of instantaneous velocity, it is nothing but you have to simply make a tangent to the path. So if this is the path in which this object is moving, so this is the path along which this object is moving. If you want to find what is the direction at point P1, then you have to simply make a tangent. At point P2, what is the direction? You have to simply make a tangent. Any other point, you have to simply make a tangent. So tangent at the path will give direction of instantaneous velocity. Why this is so? Because point P2 and point P1 are coinciding. As they are coinciding, the direction of velocity is nothing but simply its tangent to the trajectory, tangent to the path is the direction of instantaneous velocity. For example, if this object is moving in this direction, so this is the path. If you want to find what is the direction at point P1, you have to simply make a tangent. So this is the direction. At this point, you have to simply make a tangent. So this is the direction. You see, direction is not constant in this case. At this point of time, this is the direction, and this point of time, this is the vertical direction. So direction is changing with time. So instantaneous velocity will have different direction. So that's why this is called instantaneous velocity. What is the direction? What is the magnitude and direction at given instant? So your magnitude is also changing and direction is also changing. So you have to give the at instant what is the magnitude and what is the direction. That is your instantaneous velocity. Now finally, we will see the instantaneous velocity in components in Cartesian coordinates. If you remember, the position vector r can be written as xi plus yz plus zk. This is the position vector r, and if I take derivative of the position vector, that is dr over dt, that gives you the instantaneous velocity. Now I can also write, so dr by dt is nothing but d by dt of xi plus yz plus zk. Now if you remember the rule of differentiation, so I have to sum and then differentiate. This is same as differentiate and then sum. So what I will do is, I will first differentiate the first term, then take the sum, then second term, take the sum, then differentiate the third term. So what we can do is, we can differentiate separately and then we can take a sum. That is here. So what we are doing is, we are first differentiating the first term. So dy dt of xi cap, and since I is a constant, I can take I outside. So this becomes simply dx by dt, or I can write dx by dt I cap. So this is my first term. Similarly, you will have other term. So dy by dt j cap and dz by dt k cap. I can write velocity vector vxi plus v by j plus vzk, and this is velocity vector. On the right side we have dx by dt I cap, dy by dt j cap plus dz by dt k cap. Now this is the expression for velocity in terms of Cartesian coordinate. So what we can do is, we can basically compare the I cap, j cap and k cap. So if you see on the right hand side, I cap term is Vx, and so basically this is left hand side, and right hand side we have dx by dt. So I can write Vx is equals to dx by dt. So this is my velocity. V by is nothing but d by dt. If you compare this term and this term. Similarly k cap, if you compare the coefficients of k cap, we can write Vz is equals to dz by dt. So this means if you have a motion in 3 dimensions, you can calculate 3 velocity components separately. That is Vx, you have to take the x component and then take differentiation. Z component, Vz, calculate the z component of position vector and take the differentiation. So this makes life easier. You don't have to work with the position vector r. You can now work with Cartesian coordinate x, y, z, and it is easy to find Cartesian coordinates x, y, z. So what we are doing, you have a complex problem of finding the position vector, but now you are basically simplifying that problem in terms of x, y, z coordinate. So this is shown in this figure. So this is your position vector xi, this is yj, and this is zk. Similarly, if you want to find velocity vector, you will have 3 components, vxi, vyj and vzk. So what will the magnitude of position vector? You have to take simply a square root of vx square, vy square plus vz square. This you can basically understand. If you see this triangle, that is this triangle, this is the hypotenuse is nothing but x square plus y square under root. Now then you have to sum with this. So this is another vector, that is z vector zk cap. If you consider this triangle and this triangle, this is again a right angle triangle because this angle is 90 degree. So this is nothing but this square plus this square, and then you have to take the under root, and this is nothing but z, and this is what, this distance is x square plus by a square. So this distance will become x square plus by a square. So this will be x square plus by a square plus z square, and then you have to take the square root. If you do the same thing with the velocity, you will get the magnitude of velocity vector, that is bx square plus by square plus bz square, and then you have to take the square root. So generally magnitude is written with this symbol. So we put two vertical lines, one left side, another right side, and that denotes the velocity, magnitude of instantaneous velocity. If you have only two-dimensional motion, Vz is 0, there is no component, there is no z component. In that case, we can simply calculate magnitude of velocity, that is Vx square plus Vy square. Finally, how we calculate the direction of instantaneous vector. So if I know I have a motion in 2 dimensions, this is x component of velocity and this is y component of velocity, and this angle is alpha. So this angle will give the angle of instantaneous velocity with the x component of velocity. So we can calculate in this triangle, you see this is Vy, then this is Vy, and this is Vx. So I can write tan alpha is equals to this component, that is Vy, and divided by this component, that is Vx. So this is my tan alpha. So we can calculate the direction of instantaneous velocity, that is at what angle the direction of instantaneous velocity is, by taking tan alpha is equals to Vy divided by Vx. So now I know magnitude of instantaneous velocity. In case of 2 dimensions, this is simply a square root of Vx square plus Vy square, and direction of instantaneous velocity, that is Vy divided by Vx. So we introduced two terms. One is average velocity, another is instantaneous velocity. Instantaneous velocity is more interesting term or generally used compared to the average velocity. So generally whenever we say velocity, this means instantaneous velocity. We hardly use term average velocity. So in next few chapters or next few problems, whenever we are saying velocity, this means instantaneous velocity. What is the velocity at that instant? What is the magnitude of velocity at a given instant? And what is the direction at that instant? That is basically instantaneous velocity. So in this lecture or in this video, we have seen what is position vector, what kind of motion we have in 2 dimensions, how we calculate position vector, how we calculate velocity vector, what is average velocity, what is instantaneous velocity, what is magnitude of instantaneous velocity, and what is the direction of instantaneous velocity. And I hope you enjoyed this video, and if you enjoyed, please share with your friends, and I will see you in the next video. Thank you.